I would like to describe Galileo's law of falling bodies. And to start, imagine we have a graph of velocity versus time. And we know that if it's accelerating, it's falling, that this will be increasing. So the velocity is increasing as it falls. And hey, look, this makes a triangle. And we know that the area under a curve, we had that in our graphing section, is going to be the distance we go. Now, if you think about it, the area of a triangle, remember, is 1/2 the base times the height, right? 1/2 base times the height. And the base of my triangle is just t. So 1/2 times the base of my triangle is t. And hey, the velocity as something is falling from our 5 sacred equations is equal to gt. And so what I've got here is 1/2 times t times gt is equal to how far I fall on x. Or basically what I wind up with is that 1/2 g t squared is equal to x. So this is the law of falling bodies. Likewise, we can come up with an algebraic derivation of the same thing. And this was seen in an earlier blog post. And how we could come up with this is we could say, hey, how far I've gone x is equal to the average velocity times time. Again, this comes back to our 5 sacred equations. So we've got the average velocity times time. That's x. Now, another definition of the average velocity is equal to the original velocity plus the final velocity divided by 2. That's just a simple average. Now, the original velocity for dropping it, that's just 0. So we don't worry about that term. So I've just got, hey, the average velocity is basically this final velocity divided by 2. Well, hey, then, I've got x is equal to the final velocity divided by 2 times t. Remember that final velocity, if we look at this, that's just gt, so x is equal to that 1/2 term times t. And again, we've got gt. So lo and behold, this is an algebraic derivation instead of a geometric one. We've got 1/2 gt squared. And really the important thing here is that what Galileo realized is that as something falls, as it's getting faster and faster and faster, the distance it falls in every second goes up with the square of a time. And remember, that's a parabola. So if we graph, so for instance, if I were to make a graph of position versus time, because we have a quadratic equation here, the graph would form a parabola. And that was one of Galileo's key ideas. And this is something that we can see in the data from our experiments, is that our graphs of position versus time should form a parabola. And looking at the quadratic coefficient of that parabola, we can find the acceleration due to gravity.